welcome to Engineering Simple. In this video, I'll show an example of how to work a problem that deals with power factor correction. So let's assume we have a three-phase induction motor load. Induction motor load connected in delta, operating at an efficiency of 75%, operating at an efficiency of 75%. So this load absorbing 90 kilowatts at a power factor of 85%, lagging. So I'm just going to write lag. This motor is connected to a line with a voltage of 2.4 kV RMS. So this is line to line voltage. So we would like to correct the power factor to 95% or 0.95 lagging. So the frequency of this system is 60 Hertz. So question 1, what is the horsepower rating of this motor? And 2, what is the VAR rating? What is the VAR, voltage amp reactive rating of a three-phase cap bank or capacitor, cap bank connected in parallel with the load to correct power factor, to correct the power factor to 95% lagging. So we want to find the rating basically of that capacitor bank. In 3, what is the capacitance? What is the capacitance of this capacitor bank? So let me just read that problem again. So we have a three-phase induction motor load connected in delta, operating at an efficiency of 75%. This motor load absorbs or consumes 90 kilowatt at a power factor of 85% lagging. So this motor is connected to a line with a 2.4 kV RMS line-to-line voltage. So now we would like to correct the power factor to 95% lagging, or 0.95 lagging. The system frequency is 60 Hz. So we would like to know the horsepower rating of this motor. Then we would like to connect a capacitor bank in parallel with the load to correct the power factor to 95% lagging. So what is the rating of that capacitor bank? Then what is the capacitance of the capacitor bank? So I think I said this in other videos. The first step is let's make a simple sketch kind of to wrap our heads around this problem. So I have a motor. It takes an input voltage and it gets an output voltage, power. And it has an efficiency of 75%. So this load draws 90 kilowatts, so that's 90 kilowatts, which is the input power. And we know efficiency is the output power divided by the input power. So the output power is equal to efficiency of the motor times the input power. Efficiency is 0.7. The input power is 90 kilowatts. So if you calculate that, you get P out is equal to 90 kilowatt, so 90 times 0.7, which is 67.5. And I would recommend watching other previous videos. What I showed, basically 1 horsepower is 745.7 watts. So P out is equal to 67.5 kilowatt. I can convert that to horsepower. So 1 horsepower is equal to 745.7 watts. So the watts will cancel out. So I'll have 67.5 times kilo, which is 1,000, times 1 horsepower divided by 745.7. And if you carry out that calculation, you get 90.52 horsepower. So that's the horsepower rating of the motor. So when you're dealing with motors, it's important to know this equation. Efficiency is the power out divided by power in, or input power. And it's also important to know this equation. 1 horsepower is equal to 745.7 watts. So if you know these two, you can deal with motor problems. So that's question number 1. Now question 2, we want to find the rating of the capacitor bank. So we have a 3-phase. So I'm just going to draw 3 lines. So the line-to-line voltage is 2.4 kV. So basically it's from here, from this line to this line, or from this line to this line, or from this line here to this line. So it's a 3-phase system. So I have a three-phase load connected in delta. So I'm just going to draw So this is the three-phase load. Then I'm just gonna connect it to the lines or feeders. Now I want to figure out the rating of the capacitor bank that can connect in parallel with the load to correct the power factor. And let's assume this capacitor bank will be in a Y configuration. So these will be in a Y and neutral will be grounded. So I want to figure out the three-phase rating of this capacitor bank. And in question number 3, I want to also find the capacitance. So if I go from here, so the load, if I draw the power triangle, so P1 is equal to 90 kilowatts. That's from the power statement. And the Q1 is equal to P1 times the tan of theta 1. And theta 1 is basically the power factor, which is the inverse cosine of the power factor. So theta 1 is the inverse cosine of 0.85, which is 31.79 degrees. So this is theta 1, 31.79 degrees. So if you substitute the values, you will get Q1 is equal to 55.78 kVAR. So this triangle here is corresponding to the load. So this is the load that is given, and this is the cap bank that I'm trying to figure out the rating for. So if I add them, since they're connected in parallel, if I add them, so the capacitor bank, if we assume it's a lossless capacitor bank, the reactive power will be negative because capacitor banks, they supply reactive power. So I basically the power triangle, because this is 0, P is 0 for a capacitor bank, that's why it only has the reactive power. That's why I'm just showing the reactive power. So so basically P1, I will just have P1 here because, so I have P1 plus the active power of the capacitor bank, which is 0, so it's just P1, which is 90 kilowatts. Then the total Q will be Q1 plus QC. So this is the power factor that I'm trying to arrive to, which is the desired power factor that we were trying to correct to is 95%. So its power factor is 0.95 lagging. So the theta equivalent to this power factor is the inverse cosine of this power factor, basically, which is 18.19 degrees, and it's lagging, so it's positive. So theta is equal to 18.19 degrees. So I have P1 is known, I have theta known. I can calculate the total Q basically using the power triangle. So if I just redraw, it's a right angle here. So I have P1 is equal to 90 kilowatts, and I have total Q with the corrected power is equal to Q1 plus QC. QC is the capacitor bank, and I calculated this theta to be 18.19. That's the power factor angle that we're trying to correct to. So if I do some trig, so tan of theta over 18.19 degree is equal to Q divided by P1. So Q is equal to P1 times tan of 18.19 degrees. And also we know Q is the sum of the Q1 plus QC. So I know QC is equal to P1 times tan of 18.19 degrees minus Q1. So QC is equal to, so P1 is 90 kilowatt times tan of 18.19 degrees minus Q1. Q1 is, I calculated 55.78 kVAR. So if you carry out the calculation, you get minus 26.21 kVAR. In the minus sign, what it says, it just says basically that the capacitor is supplying the reactive power. So that is the size. That's the size of the capacitor bank. Now number 3, we're trying to calculate the capacitance. We know reactive power of the capacitor bank is equal to voltage squared divided by reactance of the capacitor bank. Which means XC is equal to V squared divided by QC. And what is XC, or reactance of the capacitor bank? It is 1, I'm just going to take magnitude. It's basically it's negative, but capacitance we know it's positive, so I'm just going to ignore the negative signs. So it's 1 over 2 pi times F frequency times the capacitance. So C from here is equal to 1 over 2 pi times F times X of C. So it's 1 over 2 pi times X of C is voltage squared divided by QC. In other words, it's QC divided by 2 pi times F times voltage squared. So C is equal to QC is 26.21. Again, don't worry about the negative sign. I'm just taking the magnitude, so 26.21 kVAR. And notice I took the 3-phase quantity, that means the voltage, I'm going to take line to line. 2 pi times frequency 60 Hertz times V squares, which is 2.4 kV squared. If I took the single phase rating of the capacitor bank, I would have to use the line to neutral or per phase voltage. So you have to be consistent. So if you carry out the calculation, you get C is equal to 12.07 microfarad. So hopefully you find this video useful. This is very important to know if you are preparing for the FE or PE exam. Thank you and have a great day.